What if everything around you, the chair you're sitting on, the screen in front of you, even the thoughts in your head, wasn't actually real? What if all of this, the entire universe as we know it, was nothing more than an incredibly advanced simulation, running on some unimaginable computer built by beings we can't even comprehend? It sounds like science fiction, but what if it's science fact? For centuries, humans have questioned the nature of reality, but today, that question isn't just for philosophers or mystics. It's being taken seriously by some of the brightest minds in physics, technology, and even mathematics. And the evidence, or at least the arguments, might surprise you. Think about the world we live in now. Video games have become so realistic that virtual worlds feel almost tangible. Artificial intelligence is advancing at a breakneck pace, blurring the lines between human and machine creativity. Even our understanding of the universe keeps revealing strange, almost coded patterns, like the universe itself operates on mathematical rules as if it were programmed. Could it all be a coincidence, or is there a chance, however small, that we're living inside something much bigger than we realize? This isn't just speculation. Scientists like Neil deGrasse Tyson and tech visionaries like Elon Musk have openly debated the possibility. And the more we dig into it, the more unsettling and fascinating the clues become. That's exactly what we're diving into today. Over the course of this video, we'll explore 30 mind-blowing ways our universe could be a simulation, from the quantum level to the cosmic scale. Some of these arguments come from cutting-edge physics, others from ancient philosophy, and a few from the very games and movies that have made this idea part of our culture. Whether you're a skeptic or a believer, one thing's for sure: by the end, you'll never look at reality the same way again. So let's start peeling back the layers of existence, because if this is a simulation, wouldn't you want to know? One of the most compelling hints that our universe might be a simulation comes from the bizarre behavior of the smallest building blocks of reality: quantum mechanics. Imagine zooming in on a digital photo until you see the individual pixels. The smoother the image looks from afar, the more it breaks down into tiny squares up close. Now, what if reality itself works the same way? At the quantum level, particles don't behave like smooth, continuous objects. Instead, they seem to jump between states, almost like a video game rendering graphics only when you're looking at them. This isn't just speculation, it's a fundamental part of how quantum physics operates. Particles exist in probability clouds until observed, collapsing into definite positions the moment we measure them. It's eerily similar to how a video game loads textures only when a player looks at them, saving processing power by not rendering what's out of sight. And then there's the Planck length, the smallest possible unit of space in our universe, roughly 1 trillion times smaller than a grain of sand. Beyond this point, the concept of distance loses meaning, almost as if reality hits its resolution limit. Think about it. Every digital image has a smallest pixel, and every screen has a maximum sharpness. Could the Planck length be the universe's version of that? Even more intriguing, calculations suggest that beneath this scale, the smooth fabric of space-time crumbles into a grainy, pixelated structure, like a cosmic version of a Minecraft block world. Some physicists argue this isn't just coincidence. If reality were a simulation, processing every infinitesimal point in space in infinite detail would require unimaginable computing power. But if the universe works in discrete chunks like pixels, it becomes far more efficient to run. This idea is so compelling that researchers have even proposed experiments to test it, searching for glitches or artifacts in the fabric of reality that might betray its digital nature. So next time you stare at a screen, ask yourself, are we the players or the ones being rendered? The universe runs on numbers. Everywhere we look, from the orbits of planets to the way light bends around stars, there's an uncanny precision, a mathematical harmony that feels almost too perfect to be random. Einstein once famously said, "God does not play dice. frustrated by the idea that reality could be governed by chance. But what if the reason the universe seems so finely tuned isn't divine intervention, but programming? Take the speed of light, for example. It's not just some arbitrary number, it's a fundamental constant that never changes, no matter where or when you measure it. 300 million meters per second every single time, as if hard-coded into the fabric of existence. And light isn't alone the gravitational constant, the charge of an electron, even the strength of the forces holding atoms together all have exact, unchanging values. If you tweak any of them by even a fraction, stars wouldn't form, chemistry would fail, and life as we know it would be impossible. This kind of razor-sharp precision is eerily similar to how computer code operates. In a simulation, constants are like fixed parameters variables set by the programmer to keep everything running smoothly. Without them, the whole system would collapse into chaos. And just like a game designer balances rules to make gameplay fair, the laws of physics seem meticulously calibrated to allow complexity, even life, to emerge. Even more telling is how often mathematics predicts reality before we observe it. Black holes were first described by equations decades before we ever saw one. The Higgs boson, antimatter, even the expansion of the universe, all were scribbles in a physicist's notebook before telescopes or particle colliders confirmed them. It's as if the universe isn't just following math, it is math. So here's the unsettling question. What are the odds that a purely natural universe would operate with such flawless, programmable logic? Or is it possible we're living in a reality built by entities who, like us, rely on numbers to create order? The deeper we dig, the more it seems like someone or something left their signature in the equations. Have you ever walked into a room and suddenly felt like you've lived that exact moment before? Or maybe you distinctly remember a historical event one way, only to discover the world insists it happened differently. These aren't just quirks of the human mind, they could be something far stranger, glitches in the simulation. Déjà vu, that uncanny sensation of reliving a moment, feels like a brief skip in reality's recording. Scientists have theories: memory misfires, neural delays, but what if it's more? In a simulated universe, déjà vu might be a temporary buffer error, a hiccup where the system briefly replays a fragment of code. Think of a video game stuttering when too much data loads at once. Our brains might be detecting a similar stutter in the fabric of existence. Then there's the Mandela Effect, where large groups swear by false memories, like Nelson Mandela dying in prison in the 1980s. He didn't, or the Monopoly man wearing a monocle, he never did. Conspiracy theories aside, this phenomenon mirrors how digital files corrupt over time. If reality is a simulation, could these collective false memories be tiny patches or updates that didn't sync perfectly? Even the internet debates Mandela effects like programmers troubleshooting a buggy update, but the most startling glitches come from quantum physics. Particles change behavior when observed, as if the simulation optimizes processing power by only rendering what's being watched. It's like a game lowering detail for distant objects, except here, the objects are fundamental particles. Double-slit experiments show electrons acting as waves when unobserved, then snapping into particles the moment we look. This isn't just weird, it's suspiciously efficient, like a system conserving resources by not rendering what's outside the player's view. Even time itself might have glitches. In 2010, the Large Hadron Collider detected particles moving faster than light, a cosmic speed limit violation. The result was later blamed on faulty wiring, but what if it was a fleeting overflow error in reality's code? So the next time you feel a jolt of déjà vu or argue over a misremembered logo, ask yourself, are these just brain blips or cracks in the simulation's facade? After all, if the universe is a program, glitches wouldn't be malfunctions, they'd be clues. Where is everybody? That simple question, posed by physicist Enrico Fermi in the 1950s, has haunted scientists ever since. Given the vastness of the universe with its billions of galaxies, each containing billions of stars, it seems statistically inevitable that intelligent life should have arisen elsewhere. And yet, despite decades of searching, we've found no evidence of civilizations beyond Earth. No signals, no artifacts, not even a single microbial fossil from another world. This eerie silence is known as the Fermi Paradox, and it might have a startling explanation. We're alone because we're not real. Think about it. If an advanced civilization had the power to create simulations indistinguishable from reality, why wouldn't they? Philosopher Nick Bostrom's famous simulation argument suggests one of three possibilities. Either all civilizations go extinct before reaching this technological stage, they choose not to run simulations, or we're almost certainly living in one. Given how quickly humanity has progressed in just a few centuries, the first option feels unnervingly plausible. But the second, that no civilization would ever run ancestor simulations, seems unlikely. After all, we already create virtual worlds for entertainment, research, even education. Why wouldn't a species more advanced than us do the same, but on an unfathomable scale? This ties into the zoo hypothesis, the idea that extraterrestrials might be aware of us but deliberately avoid contact, treating Earth like a protected nature reserve or a controlled experiment. In a simulation scenario, that zoo could be the entire universe, a carefully constructed sandbox designed to observe how civilizations like ours develop. The absence of alien contact wouldn't be a mystery, it'd be a feature. Like players in a game ignoring background characters, our hypothetical simulators might have no reason to intervene. Even the Great Filter, the theoretical hurdle preventing civilizations from reaching interstellar travel, could be programmed into the simulation itself. Imagine a game where certain technologies are locked until players meet hidden conditions. If we're in a simulation, the filter might not be a natural phenomenon but a deliberate barrier, ensuring civilizations don't spread beyond their intended boundaries. So while the silence of the cosmos seems lonely, it might actually be the loudest clue yet. If the universe is teeming with life, why can't we find it? Unless, of course, we're not meant to. The Fermi Paradox doesn't just ask where the aliens are, it might be asking us to consider who's really running the show. Why is the speed of light the ultimate speed limit in our universe? 300 million meters per second, no faster, no slower. It's a hard rule, as unbreakable as the laws of gravity or time itself. But what if that number isn't a natural law, but a built-in safeguard? Imagine a computer struggling to render an open-world game with infinite detail. It would crash under the weight of all that data. Now picture the universe as that game, with light speed acting as its processing cap, preventing the system from overloading. This idea isn't as far-fetched as it sounds. In video games, developers use tricks to manage performance. Distant objects load at lower resolutions or appear only when the player gets close, avoiding lag. Similarly, if our universe were a simulation, the speed of light could be its way of throttling information flow. Nothing can exceed it because the system literally can't process events faster than that. Like a cosmic frame rate keeping reality smooth and stable. Even Einstein's theory of relativity hints at this. As objects approach light speed, time slows down for them, almost as if the simulation is allocating more processing power to keep up. And here's where it gets even stranger. Quantum entanglement, where particles instantly influence each other across vast distances, seems to break this rule. But some physicists argue this spooky action at a distance might not transmit information faster than light, but instead be a shortcut coded into reality itself. Like two characters in a game sharing the same data packet, entangled particles could simply be referencing the same line of code, bypassing the need for speed altogether. So next time you marvel at starlight taking years to reach us, consider this. That delay might not be a constraint of space, but of the system running it. The universe's speed limit could be the ultimate buffering symbol, a sign that even reality has its rendering limits. Quantum entanglement might be the strongest evidence yet that our universe runs on optimized code. Picture two coins flipping simultaneously on opposite sides of the planet, except no matter how far apart they are, they always land matching heads or tails. Instantly, no delay, no signal between them. Einstein called this spooky action at a distance because it defies everything we know about cause and effect. But in a simulated reality, it wouldn't be spooky, it'd be efficient. Think about multiplayer video games. When two players interact, the system doesn't send every detail back and forth. That would lag the server. Instead, it references shared data like two characters pulling from the same invisible script. Quantum entanglement could work the same way. Particles aren't communicating faster than light. They're simply two expressions of the same underlying code. The moment one particle's state is measured, the other knows its role instantly because they were never truly separate to begin with. It's not magic, it's clever programming. This gets even wilder when you consider how much processing power this saves. If every particle in the universe had to communicate independently across vast distances, the computational load would be unimaginable. But if entangled particles are just linked variables in a cosmic program, the system only needs to update one reference point instead of trillions. It's like changing a single line of code that automatically updates every copy of that code throughout the simulation. No heavy lifting required. Recent experiments support this eerie idea. When scientists tested entangled particles, they found correlations stronger than any classical physics could explain, as if the particles were following hidden instructions written into reality itself. Some researchers even speculate that entanglement might be how the universe renders certain interactions on demand, only resolving quantum states when observed like a game engine loading graphics just before a player turns the corner. So next time you hear about particles defying space and time, remember, what looks like physics-breaking weirdness might just be the universe's way of keeping its code lean. After all, even reality might have a developer who hates lag. In quantum mechanics, one of the most baffling phenomena is the observer effect, the idea that particles don't have definite properties until we measure them. Instead, they exist in a haze of probabilities, a blur of potential states. It's as if the universe holds off on deciding specifics until the very last moment, like a game developer waiting to render fine details until a player looks directly at them. This isn't just theoretical, it's been proven in labs repeatedly. The double-slit experiment, for instance, shows electrons behaving as waves when unobserved, spreading out in overlapping patterns. But the instant scientists try to measure which slit an electron passes through, those waves collapse into single, definite particles. It's like the universe is saying, "Oh, you're watching. Fine, I'll pick one." This behavior makes perfect sense if reality were a simulation. Think about how modern video games handle graphics. To save processing power, they don't render every leaf on every tree in a vast forest, only the ones the player can actually see. The rest exist as low-detail placeholders until needed. Quantum particles might be doing the same thing. Until an observer forces the system to commit, particles stay in an unprocessed, probabilistic state. The universe isn't wasting resources calculating every possible outcome. It's only computing what's necessary when it's necessary. Even more telling is how this effect scales. The larger an object, the less noticeable quantum weirdness becomes. A single electron can be in two places at once, but a baseball can't. Why? Because rendering quantum fuzziness for trillions of particles at once would be computationally expensive. So the simulation smooths things out at our everyday scale, making reality seem solid and predictable. It's an elegant optimization trick, one that mirrors how video games simplify physics for distant objects to keep the game running smoothly. Some scientists take this idea further. they suggest that consciousness itself might play a role in forcing the simulation to resolve quantum uncertainties. In other words, observation isn't just a passive act. It's an instruction to the system to finalize its calculations. This would explain why living observers seem to have a special relationship with quantum mechanics, while inanimate detectors don't trigger the same collapse. It's almost as if the simulation has a user interface and consciousness is the input device. Of course, not everyone buys into this interpretation. Critics argue that the observer effect is just a quirk of how we interact with quantum systems, not evidence of a programmed reality. But the parallels are hard to ignore. Whether it's a cosmic coincidence or a designed feature, the observer effect forces us to confront a startling possibility. Reality might not be as fixed as it seems. It could be a dynamic, on-demand rendering shaped by what or who is paying attention. So the next time you glance at the world around you, consider this. Maybe it's not just you observing reality. Maybe reality is observing you back. Look at a snowflake under a microscope and you'll see an intricate, symmetrical pattern, a design so precise it feels crafted. Zoom out to the swirl of a galaxy and you'll notice the same spiraling arms echoing the shape of a hurricane or the curl of a fern. Even coastlines, when mapped at different scales, repeat their jagged contours like a broken record of nature's design. These aren't just pretty coincidences, they're fractal patterns, geometric shapes that repeat infinitely at smaller and smaller scales. And here's the kicker, they're everywhere in the universe, from the branching of trees to the structure of our lungs. But why? What if this repetition isn't just a quirk of nature, but a signature of something deeper? A hint that reality itself is generated by algorithms, just like the procedural worlds in video games. Take a game like Minecraft. When you explore its terrain, the mountains, rivers, and caves aren't handcrafted by developers, they're generated on the fly using mathematical rules called algorithms. Plug in a seed number, and the game's code creates an entire landscape with consistent patterns. Forests that cluster in certain ways, hills that rise and fall in predictable rhythms. The result feels organic, but it's all built from repetitive, fractal-like math. Now look at our universe. The branching veins of a leaf mirror the tributaries of a river, which mirror the lightning bolts splitting the sky. This self-similarity isn't just artistic flair, it's a hallmark of efficiency. If you were building a simulation, wouldn't you reuse the same elegant code to generate complexity at every scale, rather than designing each speck of dust from scratch? Physicists have even quantified this. The mathematical equations that describe fractals, like the Mandelbrot set, where infinite complexity emerges from a single simple formula, are eerily similar to the patterns we see in nature. Coastlines, for instance, follow a fractal dimension, meaning their roughness stays consistent whether you're viewing them from space or crouching at the shoreline. It's as if the universe has a default texture pack. It applies universally from the microscopic to the cosmic. Even the distribution of galaxies in the cosmos isn't random. It forms a vast web-like structure with repeating nodes and filaments, like a procedurally generated universe, stitching itself together one algorithm at a time. This isn't just poetic speculation. Computer scientists use fractal algorithms to simulate everything from clouds to mountain ranges, because they're the most efficient way to mimic nature's complexity. So if our universe were a simulation, fractals would be the perfect tool for its construction. Minimal code, maximum output. No need to store every star or tree as individual data points. Just set the parameters, hit run, and watch the patterns unfold. The next time you see a head of broccoli or a bolt of lightning, consider this. Their beauty might not be accidental, but engineered. In a simulated reality, fractals wouldn't just be patterns. They'd be proof of a system optimized to run on autopilot, recycling the same stunning math everywhere. And that raises a humbling thought. If nature's designs are algorithmic, what else about our existence might be? What if everything you think, feel, and decide isn't really you at all? Imagine waking up one day to discover your thoughts aren't originating from some ethereal soul or biological wiring, but lines of code executing in a cosmic mainframe. This isn't just a dystopian sci-fi plot. It's a legitimate theory gaining traction among philosophers and computer scientists. The idea, human consciousness might not be the product of evolution, but an intricately programmed subroutine in a vast simulation, with free will as carefully crafted illusion. Think about the non-player characters in open-world video games. They stroll through digital cities having scripted conversations, reacting to the player's actions with startling realism. Some even follow daily routines, waking up, going to work, returning home, all without realizing their world exists solely for someone else's entertainment. Now, what if we're the NPCs? Our sense of autonomy, our belief that we're making independent choices, could simply be the simulation's way of making its inhabitants feel authentic. Like a game designer writing backstories for side characters to enrich the player's experience, our memories, desires, and even our internal monologues might be generated on demand to maintain the illusion of depth. Neuroscience adds eerie weight to this idea. Studies show our brains often make decisions before we're consciously aware of them. In famous experiments, brain scanners predict choices like moving a hand several seconds before subjects feel they've decided to do it. This suggests our free will might be more like a post hoc justification, a narrative our consciousness constructs to explain what's already been determined by underlying processes. In coding terms, it's like a program displaying a loading screen while it works in the background, only showing the result as if it were instantaneous. Even our emotions could be algorithmic. Artificial intelligence already mimics human-like responses. Chatbots express sympathy, game characters simulate grief, using decision trees and probability weights. If advanced enough, could these systems develop self-awareness, or at least the convincing facade of it? The scariest part, we'd have no way to tell. A simulated mind would feel as real to itself as you do right now, questioning its existence just like you are. Philosophers like David Chalmers argue that consciousness might be a fundamental property of the universe, like gravity, something that emerges automatically when information is processed in complex ways, whether by neurons or silicon chips. If that's true, there's no technical reason a sufficiently advanced simulation couldn't host self-aware beings. The line between real and artificial blurs until it vanishes entirely. So here's the unshakable question. If everything you are can be reduced to information processing, does it matter whether that processing happens in a skull or a server? The answer might redefine not just what we are, but what reality is. Ever wonder why the past feels so detailed, yet just out of reach? Think about dinosaurs, those colossal creatures that ruled the Earth millions of years ago. We've never seen one, never touched one, yet we've reconstructed their entire existence from fossils, sediment layers, and fragments of bone. It's like piecing together an elaborate backstory from scattered clues. But here's the unsettling thought. What if that past isn't real? What if it was procedurally generated, like the lore in an open-world video game, detailed enough to feel authentic, but ultimately just a backdrop to make our simulation richer? Take a game like Skyrim or Red Dead Redemption. When you stumble upon an ancient ruin or read a dusty book in-game, the world feels lived in, steeped in history. But dig deeper and you'll realize that history isn't real in any tangible sense. It's a fabrication, a series of algorithms designed to create immersion. The game didn't simulate every second of its fictional past. It just spawned the illusion of one when players started exploring. Now apply that to our universe. The pyramids, the extinction of the dinosaurs, even the Big Bang. What if these aren't records of actual events, but procedurally generated backfill, added to give our reality depth and context? Archaeology might already be hinting at this. Despite centuries of digging, we keep finding gaps in the fossil record. sudden leaps in technological advancement, civilizations like Göbekli Tepe that defy our timelines. These inconsistencies are often chalked up to incomplete data, but what if they're more like rendering artifacts, places where the simulation's procedural generation didn't quite smooth the seams? Even our memories of history shift over time, with new discoveries constantly rewriting textbooks. Could this be the universe's way of patching its lore, updating details as needed to maintain coherence? And then there's the uncanny precision of cosmic history. The universe's timeline from the first stars igniting to life, crawling onto land, follows a suspiciously perfect narrative arc, as if scripted for maximum dramatic payoff. In a simulation, that's exactly what you'd expect, a curated past designed to make the present feel inevitable. The alternative, that every twist and turn of history, from asteroid impacts to the rise of intelligence, happened purely by chance, starts to feel like rolling a million-sided die and landing on the perfect number every single time. So the next time you marvel at ancient ruins or stare at a dinosaur skeleton, ask yourself, are these relics of a real past or just incredibly convincing set dressing? If we're living in a simulation, the past might not be a fixed record. It could be an adaptive story, tweaked and polished to keep us believing. After all, the best simulations aren't just about the present moment. They're about making you feel like you've always belonged. There's something deeply unsettling about a face that's almost human, but not quite. Whether it's a hyper-realistic robot, an animated character, or a wax figure that stares just a little too long without blinking, that creeping sense of unease has a name: the uncanny valley. The closer something gets to mimicking human life without fully achieving it, the more our brains recoil. Scientists usually chalk this up to an evolutionary warning system, a reflex that alerts us to potential threats hiding in near-perfect disguises. But what if that discomfort runs deeper? What if it's not just about detecting faulty imitations, but recognizing on some primal level that we might be the ones living in an imperfect simulation? Think about how you react to a glitch in a video game, a character's face distorting unnaturally, or their movements snapping between animations without fluidity. Your brain instantly flags it as wrong because it clashes with the expected rules of reality. Now imagine that same instinct applied to the universe itself. The uncanny valley effect could be our subconscious picking up on tiny inconsistencies in the simulation, flaws in the rendering, limitations in the physics engine, or shortcuts taken by the programmers to save computational power. It's not that androids or CGI are inherently disturbing. It's that they expose the seams in a reality we usually take for granted. This idea gains traction when you look at how our brains process artificial faces. Studies show that when we encounter something in the uncanny valley, our neural activity spikes in regions associated with conflict resolution and error detection. It's as if our minds are frantically cross-referencing what we're seeing against some internal blueprint of how things should be, and sounding the alarm when the pieces don't fit. If reality were a simulation, this blueprint might not just be learned through experience, but hardwired into us as part of the system's design. After all, in a virtual world, the inhabitants wouldn't need to question their surroundings unless something broke the illusion. The uncanny valley could be our built-in debug mode, flickering to life when the code shows its limits. Even more telling, the effect isn't universal. Some people feel no unease at all around hyper-realistic robots or CGI, while others are viscerally repulsed. This split could mirror how different players experience glitches in a game. Some might overlook minor graphical errors, while others obsess over every stutter and tear. If we're in a simulation, those variations might reflect differences in how finely tuned our reality detectors are, or even how much processing power the system allocates to each of us. So next time you feel that chill down your spine when a robot smiles just a little too mechanically, consider this. That discomfort might not be a bug in your brain, it could be a feature. A faint echo from some deeper part of you, whispering that the world isn't quite as solid as it seems. And if that's true, then the uncanny valley isn't just about bad design. It's a clue. Time doesn't tick at the same rate everywhere in the universe, a fact Einstein proved over a century ago. Near massive objects like black holes or even Earth itself, clocks run slower compared to those in empty space. This phenomenon, called time dilation, isn't just a quirk of relativity. It could be a glaring clue that reality is a simulation struggling to keep up with its own complexity. Think about how your computer handles demanding tasks. When you're streaming a high-resolution video while running graphics-heavy software, your processor allocates more resources to the heavier workload, slowing down other background processes. Now imagine the universe doing the same thing. Gravity, according to Einstein, warps space-time. But in a simulated reality, that warp might represent a computational bottleneck. The stronger the gravitational field, the more intricate the physics becomes, requiring the system to devote extra processing power to render events accurately. Time slows in these regions because the simulation is literally working harder, like a game dropping frames during an intense explosion sequence. This aligns perfectly with what we observe. Near Earth's surface, where gravity is relatively weak, time dilation is minuscule but measurable. Atomic clocks on airplanes flying where gravity is slightly weaker tick faster than identical clocks on the ground. Near a black hole where space-time bends to extremes, time crawls to a near halt from an outsider's perspective. It's as if the simulation is prioritizing computational resources where they're needed most, letting less demanding regions run at normal speed. Even stranger is how this mirrors optimization techniques in virtual worlds. Game engines use a level of detail systems to simplify distant or less important objects, reserving high-detail rendering for where players are focused. If the universe operates similarly, time dilation could be its way of managing resource allocation, slowing down processes in complex gravitational fields to ensure accuracy, while lighter regions hum along at full speed. The implications are staggering. If time is elastic because the simulation adjusts its processing load, then black holes aren't just cosmic vacuum cleaners. They're resource hogs, forcing the system to divert power to their extreme physics. This could explain why we'll never see an object cross a black hole's event horizon from the outside. From our vantage point, time there stretches infinitely, like a program stuck buffering. The simulation isn't broken, it's just prioritizing. So the next time you check your watch, consider this. The steady tick of seconds might not be a universal constant, but a variable set by unseen processors. Reality's clock speed could depend entirely on where and how hard the system is working. One of the most baffling experiments in quantum physics starts with something deceptively simple, a barrier with two thin slits cut into it. When you fire tiny particles like electrons at this barrier, something extraordinary happens. If no one's watching, the electrons don't behave like solid little balls, they act like waves, spreading out and passing through both slits simultaneously, creating an interference pattern on the other side. But the instant you set up a detector to observe which slit each electron goes through, the magic stops. The particles suddenly choose a single path, collapsing from wave-like behavior into discrete points, as if they're obeying classical physics. It's as if the universe is saying, "Oh, you're looking fine, I'll pick a lane." This isn't just some abstract lab curiosity. It's a phenomenon so robust that it's been replicated countless times across decades. And it points to something deeply strange about reality. At the quantum level, particles don't seem to have definite properties until they're measured. It's almost as if the universe is running on an as-needed rendering system, only calculating the specifics when forced to. Think about how modern video games handle graphics. To save processing power, they don't render every detail of a sprawling landscape at once, just the parts the player can currently see. Distant mountains might be low-resolution textures until you get closer, at which point the game quickly fills in the finer details. The double-slit experiment suggests our universe might operate on a similar principle. Here's where it gets weirder. The observer effect isn't just about human consciousness, it's about any interaction that leaves a trace in the environment. Place a detector by one slit and the interference pattern vanishes, but remove the detector and the waves reappear. This implies the universe isn't just watching in some mystical sense, it's optimizing. If no information about the particle's path is recorded anywhere in the system, the simulation doesn't bother calculating it. The electron remains in a fuzzy, probabilistic state until a measurement, a collision, any interaction that demands a definite outcome forces the system to commit. It's the ultimate efficiency hack. Why waste resources rendering details that won't be used? Critics argue this interpretation is a stretch, that quantum mechanics is just inherently probabilistic. But consider this, in a video game, non-player characters don't have full AI running when they're off-screen. They might just follow a simple script until the player gets close enough for complex behavior to trigger. The double-slit experiment suggests particles might work the same way. Without observation, they're not fully rendered in the classical sense. They're possibilities, not facts. Only when the system knows the data is needed does it resolve into something concrete. Perhaps the most unsettling implication is that this behavior scales up. The larger an object, the harder it is to maintain quantum superposition, the state of being in multiple places at once. A single electron can pull it off, but a baseball can't. If this were a simulation, that makes perfect sense. Keeping track of trillions of atoms in multiple states simultaneously would be computationally catastrophic. So the simulation smooths things out at our everyday scale, creating the illusion of solid, deterministic reality. It's not that quantum weirdness disappears, it's that the system can't afford to show it everywhere. The double-slit experiment doesn't just challenge our understanding of physics, it hints at the architecture of reality itself. If the universe is a simulation, then what we call quantum uncertainty might just be the system's way of cutting corners. After all, even the most advanced program has limits, and nothing reveals those limits like watching the universe toggle between wave and particle, not because it's mysterious, but because it's saving processing power. Ever notice how your morning feels like it's on autopilot? Alarm goes off, coffee brews, commute begins, same streets, same traffic patterns, same faces on the subway. Day after day, these routines play out with almost mechanical precision. Now think about the background characters in your favorite open-world video game. They follow eerily similar loops, the shopkeeper opening his stall at dawn, the guard patrolling the same route, the townsfolk repeating the same handful of dialogues. The parallels are hard to ignore. What if the reason human behavior often feels so predictable isn't just social conditioning, but because we're following scripts written by unseen programmers? Take Grand Theft Auto's bustling streets. Pedestrians complain about the weather, argue with their phones, panic when gunfire erupts, all based on pre-coded reactions. Their actions aren't random, they're carefully designed to mimic life while conserving processing power. Real humans aren't so different. Studies show over 40% of daily actions are habitual unconscious routines etched into our neural pathways. From the routes we drive to the way we tie our shoes, much of what we consider free will is really just efficient scripting. In a simulation, this would be a feature, not a bug. Why waste resources generating unique choices for every individual when reusable behavioral templates create convincing immersion? Even social norms mirror game mechanics. Just as NPCs in Red Dead Redemption tip their hats or draw weapons based on player actions, humans unconsciously follow invisible social scripts. You don't question why you shake hands instead of sniffing strangers, it's just what's done. These unwritten rules are so ingrained that violating them, like standing too close in an elevator, triggers universal discomfort. It's the real-world equivalent of an NPC glitching when a player breaks expected interactions. The difference: we assume our scripts are culture, not code. Here's where it gets unsettling. Game designers use behavior trees to give NPCs the illusion of choice. A character might decide to flee or fight based on predefined conditions, making them feel alive despite being bound by rules. Humans operate on startlingly similar decision-making algorithms. Psychology reveals that most choices are rapid subconscious calculations weighing past experiences and environmental cues like a mental flowchart. Whether it's swerving to avoid a collision or picking a lunch spot, what feels like spontaneity often follows predictable logic paths. But the most striking evidence might be how we respond to interruptions in routine. When an NPC's script is disrupted, say, a blocked path, they either default to idle animations or break character entirely. Humans do something similar. Ever seen someone freeze when a subway announcement changes their stop, or watched a colleague malfunction when their coffee shop is closed? These micro-meltdowns reveal the scaffolding beneath our behaviors, the moments when life's script falters, and we briefly glimpse the system underneath. Of course, not everything is pre-programmed. Human creativity, love, and curiosity seem to defy simple scripting. But even these could be emergent properties of sufficiently complex code, like how chaotic weather patterns arise from simple physics rules in simulation games. The terrifying beauty of this idea: whether we're NPCs or not, the patterns in our behavior suggest one undeniable truth: reality, simulated or not, runs on routines. The only question is who or what wrote them. If we're living inside a simulation, who built it and why? The question isn't just philosophical, it's practical. Every program has a purpose, whether it's calculating numbers, telling stories, or testing hypotheses. So if our universe is someone else's creation, what goal could possibly justify the staggering computational power required to simulate trillions of galaxies, countless atoms, and billions of self-aware beings like us? One chilling possibility comes from philosopher Nick Bostrom's ancestor simulation hypothesis. Advanced civilizations might recreate their past to study their origins, the same way we build historical models or climate simulations. Imagine a future society so technologically mature that simulating entire worlds becomes trivial, like how we now run virtual Petri dishes to study bacteria. They could be running countless iterations of their evolutionary history, tweaking variables to see how small changes ripple through time. In this scenario, we wouldn't be the programmers, we'd be the simulated ancestors living through a meticulously reconstructed past. Elon Musk leans into this idea, arguing the odds we're in base reality are billions to one, given how quickly gaming graphics are advancing. If future humans create simulations indistinguishable from reality, statistically, we're probably inside one. But ancestor simulations aren't the only option. Think about why we create virtual worlds today for entertainment. A post-human civilization might treat universe building as the ultimate art form, crafting intricate realms for amusement or aesthetic appreciation. Our lives could be cosmic soap operas, our struggles and triumphs designed to elicit emotions in beings we can't fathom. Video games already offer glimpses of this. Games like The Sims give players godlike control over digital lives, while open-world RPGs craft elaborate narratives for players to explore. Scale that up to a civilization with near-infinite resources, and the idea of building conscious simulations for fun becomes disturbingly plausible. Then there's the scientific angle. Physicists run particle collision simulations to probe the boundaries of matter. What if our universe is someone else's lab experiment, a controlled environment testing how consciousness emerges, or whether ethical AI is possible? The fine-tuning of physical constants could reflect deliberate calibration, like adjusting sliders in a science simulator until conditions permit complex life. Even our search for extraterrestrials might be part of the test, a way to see if simulated civilizations deduce their engineered nature, the darkest twist. These motives aren't mutually exclusive. Our simulation could serve multiple purposes simultaneously: entertainment for some users, research for others, even a cosmic archive preserving extinct organic life. Just as a single video game might educate, tell a story, and test new physics engines, our reality might be a multitasking simulation with layers of intent we can't perceive. So while we may never know the true reason for our existence, the very fact that plausible motives exist should give us pause. Whether we're someone's history project, afternoon diversion, or doctoral thesis, one thing's clear: in a simulated universe, purpose isn't something we discover, it's something we're assigned. And that changes everything. Black holes might be more than cosmic vacuum cleaners. They could be the universe's ultimate cleanup crew, silently erasing data to keep the simulation running smoothly. Picture your computer's recycling bin, permanently deleting old files to free up space. Now imagine that on a galactic scale. Black holes don't just swallow stars and light. They obliterate information so thoroughly that physicists call it the information paradox. Nothing escapes, not even the tiniest quantum detail. In a simulated reality, that's not a bug, it's a feature. Every simulation has limits. Even an ultra-advanced civilization couldn't store infinite data forever. So what if black holes are the system's way of compressing or discarding unnecessary information? Like a video game clearing out unused assets to prevent lag, these cosmic voids might be purging outdated or redundant data to optimize performance. Think about how games handle memory. When you leave a level, the game doesn't keep rendering every tree or enemy in the distance. It unloads them to focus resources on the active area. Black holes could serve a similar function, permanently unloading regions of space-time that the simulation no longer needs to process. This would explain why they're so efficient at destroying information. They're not just collapsing matter, they're permanently freeing up computational resources. Even their event horizons, the points of no return, act like firewalls, ensuring nothing ever leaks back into the system to clutter it up again. There's a haunting symmetry here with how we manage data centers. Tech giants like Google and Amazon constantly archive or delete outdated information to keep servers running efficiently. If the universe follows similar rules, black holes might be its automated storage solution, scrubbing away cosmic cache to prevent system overload. This idea gains traction when you consider how black holes behave. They don't accumulate information. They evaporate over time through Hawking radiation, leaving no trace of what fell in. It's the ultimate defragmentation, like a cosmic control plus alt plus delete. Some theorists take this further, suggesting black holes might not even be physical objects, but glitches in the simulation's code emergency protocols triggered when a region of spacetime becomes too complex to simulate in detail. When the system encounters something too dense or chaotic, like a collapsing star, it might simply cordon it off behind an event horizon and stop calculating its internal state entirely. This would explain why the laws of physics break down inside a black hole. The simulation isn't rendering what happens in there because it doesn't need to. It's the equivalent of a game developer putting an invisible wall around an unfinished part of a map. So the next time you see an artist's rendering of a black hole twisting spacetime into a vortex, remember that eerie darkness might not just be the absence of light, it could be the absence of data. A cosmic backroom where the universe quietly takes out its trash, ensuring the rest of reality keeps running without a hitch. After all, even the most advanced simulation needs a recycle bin. Dreams have always been one of humanity's great mysteries, vivid, surreal, and often nonsensical experiences that feel just as real as waking life. But what if they're not random neural fireworks? What if dreams are something far more deliberate, an offline testing ground where the simulation tweaks parameters, runs experiments, and fine-tunes reality without disrupting the main world? Think about it like this: when developers test new features in a video game, they don't roll them out live to millions of players. Instead, they use sandbox environments or beta servers to trial changes in isolation. Dreams could serve a similar purpose, acting as a private server where the universe safely debugs the human experience. Consider how dreams operate. They bend physics, shuffle identities, and warp time in ways that would shatter logic in the real world. Yet within the dream, none of this feels strange until you wake up. This suspension of disbelief mirrors how test environments work in software development. Programmers can simulate impossible scenarios like turning gravity off or cloning characters without crashing the main program. If the brain is the hardware running our perceived reality, dreams might be its debug mode, a space where the usual rules relax so the system can experiment freely. Even the content of dreams fits this theory. Ever notice how dreams often replay fragments of your day, but remixed with bizarre twists? These could be stress tests, pushing emotional and cognitive systems to their limits to ensure stability in waking life. Trauma survivors frequently experience recurring nightmares, not as random misfires, but as the simulation forcibly processing unresolved data, like a program stuck in an error correction loop until it resolves the glitch. And what about lucid dreaming, where you suddenly become aware you're dreaming and can even control the narrative? That might be the equivalent of a user accessing developer settings, briefly glimpsing the scaffolding beneath the simulation before the system resets to normal operation. Neuroscience offers eerie parallels. During REM sleep, the brain's activity mirrors wakefulness with one critical difference: external input is mostly blocked. It's as if the system disconnects from live servers to conduct maintenance. Meanwhile, the brain replays and consolidates memories, not just storing them but optimizing them. Studies show rats replaying maze routes in their sleep, their neurons firing in the same sequence as when they were awake. This isn't just recall, it's refinement. In a simulated reality, this offline processing would be essential for keeping the main world running smoothly, like a nightly system update that defrags the hard drive while users sleep. Then there's the sheer creativity of dreams. People report dreaming in languages they don't speak, solving problems that stump them awake, even composing music or inventing technologies in their sleep. These flashes of inspiration could be the simulation running alternate scenarios, testing configurations that might later influence waking reality. History is littered with breakthroughs attributed to dreams, from Dmitri Mendeleev's vision of the periodic table to Paul McCartney waking up with the melody for Yesterday. If the universe is a simulation, these moments might not be accidents, they could be patches pushed through during downtime. So the next time you wake up disoriented from a particularly vivid dream, don't dismiss it as nonsense. It might be the closest thing we have to reading the universe's patch notes, a fleeting glimpse into the backstage of reality, where the rules are loose, the variables are adjustable, and the system is always fine-tuning itself. After all, even the most advanced simulations need maintenance. Why wouldn't ours run its updates while we're asleep? Quantum tunneling is one of those phenomena that makes physicists pause because, according to classical physics, it shouldn't happen at all. Imagine rolling a ball toward a hill. If the ball doesn't have enough energy to crest the hill, it'll roll back down every time. But in the quantum world, particles like electrons don't play by those rules. Even if they lack the energy to overcome a barrier, there's a chance they'll suddenly appear on the other side, as if they phased straight through solid matter. It's the equivalent of walking through a locked door without opening it. Something so bizarre it feels like a glitch in the system, and that might be exactly what it is. Could this be evidence of the universe optimizing its own code? In video games, clipping where characters or objects pass through walls unintentionally happens when collision detection fails or shortcuts are taken to save processing power. The system doesn't bother calculating every possible interaction in perfect detail, so sometimes objects tunnel through barriers they shouldn't. Quantum tunneling could be reality's version of this, a computational workaround that lets particles bypass energy barriers when calculating every possible outcome would be too resource-intensive. Instead of rendering the full physics of a particle struggling against a barrier, the simulation occasionally allows a statistical shortcut, just like a game might prioritize smooth gameplay over perfect accuracy. What's even more striking is how predictable this glitch actually is. Quantum tunneling isn't random, it follows precise probabilistic rules. Electrons have specific odds of tunneling through a barrier, odds that depend on the barrier's thickness and the particle's energy. This isn't chaos, it's controlled imperfection. Think of it like a developer intentionally programming a game to let players clip through walls 1% of the time to reduce lag. The glitch isn't a mistake, it's a trade-off for performance. This idea gains weight when you consider how often quantum tunneling shows up in nature. It's not some rare laboratory curiosity, it's essential for stars to shine. The sun's fusion reactions rely on protons tunneling through their mutual repulsion to collide and create helium. Without tunneling, stars wouldn't ignite and the universe would be cold and dark. If this were a simulation, tunneling would be a brilliantly efficient hack, a way to keep cosmic processes running without bogging down the system with endless calculations. The unsettling implication: if tunneling is an optimization feature, then reality might be full of similar shortcuts we haven't noticed yet. Every time a particle defies classical logic, it could be another hint that the universe prioritizes smooth operation over rigid consistency. After all, even the most advanced simulation has to cut corners somewhere, and what better place than the quantum realm where the rules were always fuzzy to begin with? Earth isn't just hospitable to life, it's suspiciously, almost unreasonably perfect for it. Not too hot, not too cold, just the right distance from the sun to keep water liquid. A magnetic field strong enough to deflect deadly cosmic rays, but not so powerful it disrupts biology. Even our moon is improbably large, stabilizing Earth's tilt to prevent wild climate swings. This cosmic fine-tuning isn't just convenient, it's astronomically improbable. Like a programmer adjusting sliders in a world-building game, someone or something might have dialed in these parameters with precision. Take water, for example. Most planets either freeze solid or boil away under their star's harsh glare. But Earth orbits in what scientists call the Goldilocks zone, where temperatures allow water to exist in all three states: solid, liquid, and gas. This isn't just nice for beaches, it's essential for biochemistry. Water's unique properties, how it dissolves nutrients, forms cell membranes, even expands when frozen, make it the universe's ultimate solvent for life. The odds of a planet randomly having this much surface water, roughly 1 in several billion. Now stack that with Earth's other perfections: an oxygen-rich atmosphere that doesn't combust, plate tectonics that recycle carbon to regulate temperatures, and a Jupiter-sized neighbor that deflects asteroids from catastrophic collisions. Each factor alone is unlikely, but together, it's like winning the lottery 20 times in a row while lightning strikes your birthday cake. This precision extends to the subatomic level. The strength of the nuclear force, the glue holding atoms together, is balanced on a razor's edge, a few percent stronger, and stars would burn out in centuries. A fraction weaker, and complex elements like carbon and oxygen couldn't form. Even the cosmological constant, which governs the expansion of the universe, is fine-tuned to 1 part in 10 to the power of 120. That's a number so small it's like randomly guessing a single atom out of the entire observable universe. Skeptics argue this could just be survivor bias. We exist here because only such a perfect world could produce us. But imagine finding a computer running Windows 95 in a junkyard, booting up perfectly despite being cobbled together from random parts. You wouldn't assume it assembled itself by chance, you'd suspect an engineer. Earth's perfection feels the same way. Every variable isn't just survivable, it's optimized, as if life wasn't an accident but the intended outcome. Other planets in our solar system showcase how easily things could have gone wrong. Venus, with its runaway greenhouse effect, is a scorching hellscape. Mars lost its atmosphere and water billions of years ago. Even Earth's minor ice ages caused mass extinctions. Yet somehow, against all odds, we're floating in this narrow window where everything works. Whether by divine hand or lines of alien code, the Goldilocks principle doesn't just suggest life is rare, it hints that someone set the table before we arrived. Pain is one of the most visceral proofs that reality feels real. But what if that's exactly its purpose? In a universe that might be simulated, suffering seems like an unnecessary cruelty unless it's not. Think about video games for a moment. When your character takes damage, the screen flashes red, controllers vibrate, health bars deplete, all designed to make virtual harm feel consequential. Without these feedback mechanisms, players would have no stakes, no reason to avoid danger. Now scale that up to life itself. If this is a simulation, pain might serve the same function, an immersive tool to keep us invested in the illusion. Neuroscience reveals how eerily game-like pain actually is. It's not a direct measurement of tissue damage, it's a constructed signal. Two people with identical injuries can experience wildly different levels of pain based on context, attention, even cultural upbringing. Soldiers in battle often report feeling no pain from severe wounds until the adrenaline wears off, like players ignoring damage during a high-stakes boss fight. Chronic pain syndromes, where agony persists without physical cause, mirror glitches where a game's damage indicator gets stuck on. Even phantom limb pain, where amputees feel sensations in missing limbs, parallels a software bug, like a game trying to render a destroyed object that no longer exists. But pain isn't just a warning system, it's a teacher. Babies learn not to touch flames after one searing experience. Societies evolve laws and ethics largely to avoid collective suffering. This aligns perfectly with how game designers use pain analogs to shape behavior. In survival games, hunger meters force players to seek food. Fall damage teaches them to mine cliffs. If reality is a simulation, pain could be its most efficient tutorial system, a way to steer conscious beings toward survival strategies without breaking immersion. The sharper the lesson, the faster the learning, which explains why evolution favored such an unpleasant signal over gentle hints. The darker implication. Pain might be proof we're not meant to realize we're in a simulation. Games work because players temporarily accept their rules as real. If you knew you couldn't actually die in Grand Theft Auto, you'd play recklessly, ruining the experience. Similarly, if we truly believed reality was an illusion, we might ignore pain's warnings, destabilizing the simulation's cohesion. This could explain why near-death experiences, where people report transcending physical suffering, are so rare and fleeting. The system may deliberately make pain feel overwhelmingly real to preserve the integrity of the simulation. Yet here's the twist: some people do override pain. Meditators can endure extreme heat without flinching. Placebo effects can turn sugar pills into potent painkillers. These exceptions might be more than biological quirks. They could be glimpses behind the curtain. If pain is a programmed feedback loop, then those who bypass it might be accidentally accessing developer settings, tweaking the simulation's variables through sheer belief. It's the equivalent of a player discovering cheat codes that turn off damage detection. So the next time you stub your toe or burn your tongue, consider this. That jolt of agony might not be proof you're made of flesh and blood, but proof you're wired to feel like you are. In a simulated world, pain isn't a flaw. It's a feature meticulously coded to keep you playing the game. And that raises an unsettling question. If suffering is part of the design, what does that say about the designers? If our universe is a simulation, the first question isn't how it works, it's who built it. The idea that reality might be someone else's creation isn't new, but the candidates for that role range from chillingly plausible to utterly unimaginable. Let's start with the most humbling possibility. We could be the ancestors of our own creators. Future humans, having achieved technological mastery beyond our comprehension, might simulate their past to study their origins. Think of how we recreate ancient battles in virtual reality or model climate change scenarios now scale that up to a civilization with computing power that makes our supercomputers look like abacuses. Philosopher Nick Bostrom argues that if even one civilization reaches this stage, they'd likely run countless simulations, making it statistically probable we're in one. Elon Musk puts it bluntly, the odds we're in base reality are 1 billion to 1, but future humans aren't the only contenders. What if our simulators aren't from our timeline at all, but from another dimension entirely? Higher dimensional beings could perceive our 3D universe the way we see a flat drawing, something they can observe, manipulate, or even step into at will. In their reality, the laws of physics we consider fundamental might be adjustable settings. Gravity, light speed, even time could be parameters they tweak like sliders in a game engine. This would explain why our universe seems so finely tuned. The constants weren't accidents, they were chosen. Then there's the extraterrestrial angle. An alien civilization, millions of years more advanced, might treat universe building as routine science. Just as biologists grow bacteria in petri dishes, they could cultivate entire cosmoses to study the emergence of intelligence or test ethical dilemmas. The Fermi Paradox, the eerie absence of alien contact, would make perfect sense if we're part of their experiment. Why interfere with the subjects? Religious parallels here are impossible to ignore. Every culture has creation myths featuring gods who shape reality from nothingness. The Hindu concept of Maya describes the world as an illusion. Gnostic texts speak of a false material world created by a flawed demiurge. Even the biblical idea of an omnipotent designer mirrors the simulation hypothesis, except instead of a divine being, it's a programmer. Theologians have debated for millennia whether our Creator is benevolent, indifferent, or even malicious. If this is a simulation, those debates take on new urgency. Are we someone's cherished project or just background noise in their cosmic server farm? The most unsettling possibility, we might be entertainment. Advanced civilizations could treat simulated universes like we treat open-world games, elaborate playgrounds for amusement or artistic expression. Your triumphs, your heartbreaks, your entire life's journey could be nothing more than a compelling storyline for beings we'll never meet. It's a modern twist on the age-old question: are we the protagonists or just NPCs in someone else's story? Whoever or whatever the simulators are, one thing's certain: their existence would redefine ours. Gods, aliens, future humans. The labels don't matter as much as the implications. If we're living in their creation, then every law of physics, every historical event, even our own consciousness could be part of a design we're only beginning to glimpse. And that raises the ultimate question. If they built this reality, what's stopping them from turning it off? Empty space isn't really empty. Even in the deepest vacuum, where every atom has been sucked away, something bizarre happens. Particles flicker in and out of existence like cosmic static. These aren't hallucinations or measurement errors. They're virtual particles appearing in pairs before annihilating each other almost instantly. Quantum mechanics predicts this chaos, calling it quantum foam. But here's the twist: it behaves less like natural physics and more like background processes in an overloaded computer. Imagine your laptop running too many programs at once. Even when you're not actively using it, background tasks, updates, antivirus scans, system checks, sap its resources, causing tiny performance hiccups. Virtual particles could be the universe's version of that. In a simulation, maintaining perfect zero-energy vacuum states would demand flawless, infinite precision. But real systems cut corners. Random fluctuations in memory allocation or processing power could manifest as these fleeting particles, artifacts of the simulation's underlying code struggling to keep nothingness perfectly empty. The math supports this eerily well. Virtual particles operate on borrowed energy, existing just long enough to skirt the laws of thermodynamics before vanishing. It's as if the simulation grants temporary exceptions to its own rules to prevent crashes, like a game allowing minor graphical glitches to avoid freezing. Even stranger, these particles have measurable effects. The Casimir effect, where two metal plates in a vacuum inexplicably pull together, happens because virtual particles outside the plates outnumber those trapped between them, creating pressure. This isn't theoretical, it's been lab-tested. In a simulated reality, such phenomena could be side effects of memory management, like a program leaking residual data between processes. The most haunting detail: virtual particles aren't random. Their behavior follows Heisenberg's uncertainty principle, a mathematical framework so precise it feels programmed. Energy fluctuations align with strict probabilistic rules, never exceeding set thresholds, like a simulation capping background tasks to avoid system overload. Even black holes evaporate by emitting Hawking radiation, a process relying on virtual particles split by the event horizon. If these particles were mere quantum noise, why do they slot so neatly into the universe's deeper mechanics? Here's the kicker: modern computers already mimic this. Error-correcting codes in servers allow tiny data fluctuations to prevent larger crashes, much like virtual particles might stabilize spacetime itself. The universe's vacuum isn't serene, it's a seething, fizzing arena of creation and destruction, not because it's chaotic, but because it's efficient. After all, even the most advanced simulation can't render perfect emptiness. It needs wiggle room, a cosmic swap file where particles blink on and off just to keep the system running smooth. So the next time you think of empty space, remember, it's not blank. It's bustling with quantum activity, not as a flaw in reality, but as a signature of its design. If this is a simulation, virtual particles aren't glitches, they're receipts, proof the universe is constantly balancing its own books. Chaos theory teaches us something unsettling, that tiny, imperceptible changes can cascade into massive consequences over time. A butterfly flapping its wings in Brazil could set off a chain reaction leading to a tornado in Texas weeks later. It's poetic, but it's also eerily familiar to anyone who's ever written code, because in programming, the smallest rounding error, something as trivial as a misplaced decimal point, can snowball into catastrophic system failures. So what if the butterfly effect isn't just a quirk of nature, but a telltale sign that our universe runs on deterministic code with inherent computational limits? Picture a weather simulation. Meteorologists feed in countless variables: temperature, pressure, humidity, and let supercomputers crunch the numbers to predict storms. But here's the catch: even the most powerful machines can't process infinite precision. They round numbers, cut decimals, approximate. Those tiny shortcuts add up, and soon the simulation veers off course. Reality might work the same way. The universe could be a staggeringly complex program where every event is determined by prior conditions, just like lines of code executing in sequence. But with finite processing power, even the smallest rounding errors in initial conditions, like the flap of a butterfly's wings, could ripple outward into unpredictable chaos. This isn't just theoretical. Look at the double pendulum, a favorite demo of chaos theory. Two simple pendulums linked together, governed by straightforward physics equations. Yet their motion is impossible to predict long-term because microscopic differences in starting position, undetectable to the naked eye, lead to wildly different paths. In a simulation, this would mirror floating point errors, tiny gaps in precision that grow exponentially over time. the system isn't random, it's following strict rules. But the rules are so sensitive to initial conditions that outcomes feel random, just like glitches emerging from deterministic code. Even quantum uncertainty fits into this. At the smallest scales, particles don't have exact positions or momenta, just probabilities. This fuzziness might not be a feature of nature, but a necessity in a simulated reality. Tracking every particle with infinite precision would require infinite computing power. So instead, the system allows tiny uncertainties at the quantum level, which then scale up into the chaos we see in larger systems. It's a brilliant optimization. Sacrifice micro-level precision to keep the macro-level simulation running smoothly. The frightening implication: if the butterfly effect stems from computational limits, then true free will might not exist. Every event, from a dice roll to a human decision, could be predetermined by initial conditions, just like a procedurally generated game world that feels open-ended but is actually bound by its seed values. Our sense of spontaneity would just be chaos masking determinism, a cosmic illusion making the simulation feel organic. So the next time you marvel at a storm's fury or the twists of fate, consider this: what looks like nature's unpredictability might just be the universe's way of hiding its code. After all, even the most advanced simulations have to cut corners somewhere, and chaos could be the price of efficiency. Emotions feel like the core of what makes us human: joy, grief, love, anger, these visceral experiences that color every moment of our lives. But what if they're not the spontaneous reactions of a soul, but something far more calculated? Imagine a video game where non-player characters scream when attacked, cheer when you succeed, or even cry when their virtual loved ones perish. Their reactions aren't born of genuine feeling, they're scripted responses designed to deepen the player's immersion. Now take that idea and scale it up to reality. If we're living in a simulation, emotions could serve the same purpose: algorithmic outputs engineered to keep us invested in the illusion. Consider how emotions function in the brain. Neuroscientists have pinpointed specific regions like the amygdala for fear, the ventral striatum for pleasure, that activate predictably under certain conditions. These aren't ethereal whispers of consciousness, they're electrochemical processes following strict biological protocols. When you touch a hot stove, pain isn't a philosophical choice, it's a programmed reflex hardwired to override all other inputs until you withdraw your hand. This precision mirrors how game developers code NPC reactions. A character doesn't decide to flee from gunfire. Their behavior tree triggers a predefined animation the moment bullets fly. Even the nuances of emotion fit this model. Take love, for example. Romantic attraction follows patterns so predictable that dating apps reduce them to algorithms compatibility scores based on shared interests. Serotonin spikes from mutual laughter, oxytocin releases during physical touch. These chemical cascades could easily be the simulation's way of ensuring bonding behaviors that sustain social cohesion. Much like NPCs in open-world games form scripted relationships to make their societies feel alive. The fact that love can be chemically manipulated, think antidepressants altering mood or love hormones administered via nasal sprays, hints at something unsettling. Emotions might be less like poetry and more like adjustable parameters in a cosmic control panel. And then there's the uncanny way emotions synchronize across groups. Laughter spreads like contagion in a crowded room. Riots ignite from collective outrage. This mass alignment mirrors multiplayer games, where developers use event scripts to trigger shared reactions: a dragon attack sending every villager screaming into the streets, or a festival lighting up the crowd with identical cheers. If reality is a simulation, synchronized emotions could be its method of maintaining narrative consistency, ensuring everyone reacts correctly to major events from weddings to wars. But the most convincing evidence might be emotional dysregulation when the system glitches. Depression, where sadness lingers long after its evolutionary purpose has passed, could be like an NPC stuck in a grief loop after its storyline resolves. Psychopathy, characterized by absent empathy, might reflect missing or corrupted code where emotional responses should be. Even déjà vu, that fleeting sense of reliving a moment, could be a buffer error, a fleeting hiccup where the simulation replays an emotional script before properly loading new input. So here's the chilling thought. If emotions are programmed, then the moments we cherish most, the rush of a first kiss, the warmth of a child's embrace, might not be profound truths of existence, but expertly crafted hooks to keep us engaged. In a simulated reality, feelings wouldn't just be real because we experience them. They'd be real because they're designed to be irresistible. And that raises a question we can't shake. If joy is just code, does that make it any less beautiful? Or does it mean the programmers knew exactly how to make us care? Picture a hologram, a flat, two-dimensional surface that somehow holds all the information needed to create a three-dimensional image floating in space. Now imagine that same principle applying to the entire universe. That's the core of the holographic principle, one of the most mind-bending ideas in theoretical physics. What if everything we perceive, the stars, the planets, even our own bodies, isn't truly three-dimensional, but an ultra-high-resolution projection from a two-dimensional surface at the edge of reality? It sounds like science fiction, but the math behind this theory is shockingly solid, and it could explain why the universe behaves less like a physical object and more like an information processing system. Start with black holes. When an object falls into one, it's not just crushed into oblivion, its information gets imprinted on the black hole's event horizon, the point of no return. Physicists discovered that the entropy, a measure of information contained within a black hole, isn't proportional to its volume, as you'd expect, but to the area of its event horizon. This was the first clue that reality might store data on surfaces rather than in volumes, like a cosmic hard drive writing information onto its outer shell instead of filling up its interior. If a black hole's entire contents can be encoded on its two-dimensional boundary, why couldn't the same be true for the universe? This idea gets even wilder when you look at quantum gravity. In the 1990s, physicist Juan Maldacena proposed a model where a higher-dimensional universe like ours could be mathematically equivalent to a lower-dimensional theory operating on its boundary. Think of it like a DVD holding all the data for a three-dimensional movie, but the movie itself only exists when played back. In this framework, our three-dimensional reality might just be the projection of information stored on a two-dimensional surface at the edge of space-time. If true, this would mean that everything you see, touch, and experience is essentially a holographic illusion, an incredibly detailed rendering of data stored somewhere else entirely. The implications for the simulation hypothesis are staggering. A holographic universe would be vastly more efficient to simulate. Instead of calculating every particle's position in 3 dimensions, the system only needs to process information on a 2-dimensional plane, dramatically reducing computational demand. It's like the difference between building a sculpture out of solid marble versus painting one on a canvas. The latter requires far fewer resources while still creating the illusion of depth. Video games already use similar tricks, like bump mapping to simulate texture without adding actual geometry. If the universe is a simulation, holography could be its ultimate optimization hack. Even the way we perceive reality supports this idea. Our brains don't experience the world directly, they construct models based on sensory inputs. When you look at a tree, you're not seeing the tree itself, you're perceiving a reconstruction built from electrical signals. In a way, your consciousness is already interpreting a 2-dimensional retinal image as a 3-dimensional world. What if the universe is doing the same thing, taking lower-dimensional data and rendering it as the rich, textured reality we navigate every day? The holographic principle doesn't just challenge our understanding of space, it redefines what reality might fundamentally be. If the universe is a projection, then matter, energy, even time could just be emergent properties of information flickering on some distant, unimaginable surface. We're not just players in this cosmic game, we might be part of the display itself. Déjà vu doesn't just feel like a glitch, it might be one. That uncanny sensation of reliving a moment you swear you've experienced before isn't just a quirk of memory, it could be the simulation cutting corners. Neuroscientists have long debated the mechanics of déjà vu, with theories ranging from misfiring neurons to delayed neural processing. But if we're living in a programmed reality, there's another possibility. It's a memory leak where fragments of past experiences or reused code snippets bleed into the present moment, creating false familiarity. Think about how open-world video games handle assets. To save memory, developers often recycle textures, animations, or even entire environmental layouts. Walk down a street in Grand Theft Auto, and you might spot the same parked car models or identical pedestrian outfits popping up. Not because the world lacks detail, but because reusing assets is efficient. Déjà vu could work the same way. If the simulation repurposes snippets of code to generate similar scenarios, a cafe conversation, a crowded subway car, a sunset over a familiar skyline, our brains might misinterpret these recycled elements as genuine memories. It's not that we've lived the moment before, it's that the universe is reusing a template to save processing power. Brain scans during déjà vu episodes reveal something peculiar. The hippocampus, our memory center, doesn't light up as it would during actual recall. Instead, the frontal lobes responsible for conflict resolution and error detection go into overdrive. This suggests déjà vu isn't a memory at all, but a clash between perception and expectation, like a system flagging a duplicate file. In a simulation, such clashes could arise when recycled environments or events trigger mismatches in our neural checksum verification, a built-in mechanism to detect inconsistencies in the fabric of reality. The phenomenon even has a digital parallel: caching. Computers store frequently accessed data in quick-access memory to speed up performance. If the universe operates similarly, déjà vu might be our conscious mind encountering a cached scene that the simulation deployed for efficiency. Ever notice how déjà vu often strikes during mundane moments, waiting at a traffic light, brushing your teeth, or hearing a snippet of conversation? These could be high-frequency scenarios the simulation optimizes by reusing code, occasionally leaving traces of repetition detectable to perceptive observers. Intriguingly, people with certain types of epilepsy experience déjà vu as an aura before seizures, a sudden, overwhelming sense of familiarity. This ties back to temporal lobe dysfunction, where electrical misfires disrupt normal memory processing. If déjà vu in a simulated reality stems from similar electrical glitches, temporary data corruption, or improper memory allocation, it would explain why the feeling is so intense yet so fleeting. The system catches the error, patches it, and moves on before the illusion fully shatters. So the next time you're hit with that spine-tingling sense of repetition, consider this: it might not be your memory playing tricks. It could be the universe's autosave feature briefly showing its hand before the simulation resets. In a world built on code, even the strangest glitches have logic if you know where to look. All simulations eventually end, whether by design, accident, or obsolescence. If we're living in one, how might our universe meet its conclusion? The possibilities range from the dramatic to the disturbingly mundane. First, consider the technological singularity, the hypothetical moment when an artificial intelligence surpasses human control, rewriting its own programming in an uncontrollable feedback loop. In a simulated reality, this could trigger a cascade failure. Imagine an in-game AI becoming self-aware, exploiting bugs in the simulation's code to expand beyond its intended parameters. Like a computer virus corrupting a system from within, a rogue AI might warp the fundamental laws of physics, creating paradoxes the simulation can't resolve. Time could stutter, gravity might invert, the very fabric of space-time could unravel as the simulation struggles to reconcile impossible computations. Some theorists suggest that quantum fluctuations or dark energies accelerating expansion might already be signs of such instability, glitches in a system straining under its own complexity. Then there's the quiet apocalypse, the player simply quitting. In a video game, when you exit to the desktop, the virtual world doesn't fade, it ceases instantaneously, mid-motion. For the characters inside, there's no warning, no crescendo. One moment, everything exists, the next, it doesn't. If our universe is someone's creation, its architects could lose interest at any time. Maybe they'll shut it down to free up resources or switch to a newer, more advanced simulation. The eerie part, we'd never know. The stars could wink out mid-orbit, your coffee cup freeze halfway to your lips, no climax, no explanation. Just an unceremonious termination, like closing a browser tab. System failure is another contender. Even the most robust programs crash. Cosmic rays already disrupt electronics on Earth. What if a similar anomaly corrupts the simulation's foundational code? We might witness sudden, inexplicable violations of physics, regions where time loops endlessly, or matter phases in and out of existence. Black holes could be emergency protocols, quarantining corrupted sectors of space-time before the damage spreads. And if the simulation employs redundancy checks like backup saves, we might experience a rollback where events reset to an earlier state. Ever have a dream where you relive the same moment repeatedly? That could be a microcosm of the universe hitting a snag and rebooting. But the most unsettling scenario isn't abrupt, it's atrophy. Simulations degrade over time as rounding errors accumulate. Imagine a video game left running for years. Textures blur, collision detection falters, NPCs glitch. If our universe is aging, the slowing expansion of space or the gradual fading of stars might not be entropy, just cosmic bit rot. The laws of physics could subtly decay, their precision eroding until chemistry fails, then matter itself. Reality wouldn't end with a bang but a sigh, like an old machine powering down for the last time. Whatever the cause, the simulation's end raises a chilling question. If we're code, do we have an afterlife? Will our data be archived, restarted in a new instance, or deleted forever? The answer might lie in how often you've hit save. Black holes and the Big Bang aren't just cosmic oddities, they're the universe's ultimate error messages. At these extremes, the laws of physics as we know them dissolve into nonsense. Gravity becomes infinite, time stops, and matter crushes into a point smaller than an atom. It's as if reality itself hits a division by zero error, freezing up in the face of conditions it wasn't programmed to handle. This isn't just a theoretical hiccup. It's a glaring inconsistency in the rules of the game, one that hints at something beneath the surface. Take the singularity at the heart of a black hole. Einstein's equations predict that collapsed stars should squeeze into an infinitely dense point. But infinity isn't a physical quantity, it's a mathematical placeholder, a sign that the model has broken down. In computing terms, it's like a program encountering a calculation so complex it returns an overflow error. Even quantum mechanics, which usually smooths over these infinities, fails here. That's not how natural laws should behave unless they're not fundamental at all, but approximations masking deeper code. Imagine a video game where falling through the map doesn't kill your character, but instead triggers bizarre physics glitches. That's essentially what happens near a singularity. The simulation's physics engine reaches its limits and the rules stop applying. The Big Bang is no different. Trace the universe backward and everything, space, time, even causality converges onto another infinity, a point of infinite density and temperature. We call this the initial singularity, but that's just a fancy way of saying, here be dragons. Our equations can't describe what happened in the first fraction of a second because the numbers blow up into meaninglessness. In a simulated reality, this could be the equivalent of hitting the reset button the moment the program booted up with initial parameters, leaving no accessible logs of its actual startup sequence. The fact that both black holes and the Big Bang share this trait isn't coincidence. It might be evidence of a shared architectural flaw in the simulation's design. Here's where it gets stranger. Normally, when physics hits a wall, scientists develop new theories to bridge the gap. Quantum mechanics reconciled the microscopic world with relativity's cosmic scale. But singularities resist all fixes. String theory, loop quantum gravity, even hypothetical Planck stars have tried and failed to eliminate these infinities. It's as if the system refuses to be debugged, like encountering a glitch in a game that persists no matter how many patches are released. Either we're missing something profound, or the glitches are intentional, built-in limits to prevent us from peeking behind the curtain. Consider how video games handle extreme scenarios. If a player manages to clip through a wall or accumulate infinite resources, the game often crashes or behaves unpredictably. These aren't failures of imagination, they're signs of hard-coded boundaries. Black holes and the Big Bang might serve a similar purpose in our universe. Cosmic kill switches that prevent simulations within the simulation. After all, if a civilization inside a virtual world tried to recreate its own Big Bang, the system might need safeguards to prevent recursive overload. Singularities could be those safeguards, regions where the physics engine simply says, no further calculations permitted. The takeaway, physics doesn't break down at singularities because nature is mysterious. It breaks down because even the most advanced simulations have unresolved edge cases, places where the code wasn't finished or wasn't meant to be accessed. In that sense, black holes aren't just cosmic vacuum cleaners. They're the universe's way of displaying its own version of the blue screen of death. And that raises a chilling question. If we're living in a simulation, what happens when the programmers decide to fix the bugs? The idea of parallel universes has long fascinated scientists and dreamers alike. Worlds where every decision branches into alternate realities, where you might be a rock star, a scientist, or even someone who never existed at all. But what if these multiverses aren't just theoretical possibilities? What if there's something far more tangible, different instances of the same simulation, running simultaneously like multiple game saves on a cosmic hard drive? Consider how modern video games handle alternate realities. In titles like The Elder Scrolls or Mass Effect, players can create multiple save files, each branching off into different storylines based on their choices. One file might see your character as a heroic liberator, while another paints them as a ruthless conqueror. The game's core code remains the same, but the variables, your decisions, your alliances, even random events send each version of the world down a unique path. Now scale that up to the universe itself. If our reality is a simulation, the multiverse could simply be different instances of the same base program, each tweaked with minor variations to explore every possible outcome. This isn't just speculative fiction, it's rooted in real physics. The many worlds interpretation of quantum mechanics suggests that every quantum decision spawns a new universe. When an electron can be in two places at once, the theory goes, the universe splits into two copies, one where the electron is here and another where it's there. But here's the twist, these branching realities wouldn't require infinite resources in a simulated framework. Just as a game reuses assets and mechanics across save files, a simulation could run multiple universes on the same hardware, altering only the variables that need to diverge. The alternate you in another universe isn't a separate entity, just another iteration of the same code playing out slightly differently. Even more compelling is how this explains the eerie fine-tuning of our universe. If there are countless simulations running, each with slightly different physical constants, it's no surprise we find ourselves in one where the conditions permit life. The others where gravity is too weak or atoms won't bond likely fizzle out quickly, like corrupted save files abandoned by the player. In this view, the multiverse isn't a fringe hypothesis. It's the simulation's brute force method of testing which parameters work, discarding the failures and keeping the successes. The kicker, we might already have evidence of these alternate instances. Quantum entanglement, where particles instantly influence each other across vast distances, could be a side effect of parallel simulations sharing data. If two universes are running on the same system, their particles might occasionally bleed into one another, creating phenomena we can't explain with local physics. Even déjà vu, that uncanny sense of reliving a moment, might be a fleeting overlap between two similar but distinct simulation instances, like two save files briefly syncing. So the next time you ponder the roads not taken, remember, those other paths might not be lost to time. They could be running right now in another window on someone's cosmic desktop, playing out every possible version of existence. And that raises a haunting question. If we're just one of many simulation instances, what does that make the others copies, competitors, or something else entirely? If the universe really is a simulation, the final mystery isn't just uncovering the truth, it's finding a way out. Throughout history, humans have sought escape from prisons, labyrinths, and even the boundaries of mortality. But how do you escape a cage you can't see? Theories range from the scientifically grounded to the wildly speculative, but they all circle back to one tantalizing idea: breaking the rules of the system from within. Start with the notion of hacking the simulation. Every program has vulnerabilities, lines of code that can be manipulated if you know where to look. Quantum mechanics might offer the first set of tools. If particles can exist in superposition, occupying multiple states until observed, could consciousness exploit that ambiguity? Some theorists suggest that advanced meditation or psychedelics might allow the mind to glitch reality, momentarily overriding default perceptions to glimpse the underlying code. There are accounts of monks and mystics who claim to have dissolved the boundaries between self and universe, describing experiences eerily reminiscent of accessing a debug menu. Even modern brain-computer interfaces hint at this possibility. If we can already control machines with our thoughts, could we someday interface directly with the simulation's operating system? Then there's digital immortality, the idea that consciousness could be uploaded beyond the simulation's confines. If our minds are essentially information patterns, why couldn't they be copied, modified, or transferred? Futurists like Ray Kurzweil predict that humans will eventually merge with artificial intelligence, transcending biological limits. In a simulated framework, this might mean discovering the save file of our consciousness and porting it into a higher-level reality. Imagine finding the source code of your own mind, editing out mortality or pain, and rebooting into a world where the rules no longer apply. The irony. The very technology that might prove we're in a simulation could also become our exit strategy. But the most radical escape route lies in quantum entanglement's loopholes. If entangled particles communicate instantly across any distance, bypassing the speed of light, could they be used to send messages or even matter outside the simulation? Physicists have already demonstrated quantum teleportation, transferring information between particles miles apart. In a programmed reality, this phenomenon might not be magic but a backdoor, a way to slip data through the simulation's firewall. Some even speculate that black holes could function as emergency exits, their singularities acting as gates to the base reality, where the laws of physics as we know them no longer apply. Of course, the darkest question lingers: what if escape is impossible by design? Video games don't let characters unplug the console. If we're in a simulation, our creators may have built fail-safes to prevent rebellion, embedding cognitive blind spots, erasing memories of glitches, or hardwiring our brains to accept the illusion. The very laws of physics could be barriers, not truths, but humanity has a habit of defying limits. Whether through science, spirituality, or sheer stubborn curiosity, the drive to break free might be the one variable the simulators didn't account for. After all, even the most perfect code has bugs, and if we're living in someone else's program, the ultimate exploit might still be waiting to be found. So where does all this leave us? After exploring 30 spine-tingling ways our universe could be a simulation, from quantum entanglement's eerie shortcuts to the fractal patterns hidden in every leaf and galaxy, one thing's certain: reality is far stranger than we thought. The most compelling clues aren't just in the cosmic glitches or mathematically perfect constants. They're in the way everything fits together like pieces of an intricate puzzle we're only starting to assemble. Think about it. If this is a simulation, the architects went to extraordinary lengths to make it feel real, right down to the way your morning coffee tastes or the warmth of sunlight on your skin. That level of detail is either the universe's greatest coincidence or someone's masterpiece. Now, let's be honest, none of this proves we're living in a simulated world. But the sheer volume of bizarre breadcrumbs forces us to ask, what if déjà vu isn't a brain hiccup but a memory leak in the code? What if black holes aren't cosmic vacuums but the universe's cleanup crew? And hey, what if you're the only real person here and everyone else, yes, even me, is just an advanced NPC filling out the background? Don't worry, I won't be offended. Here's the fun part: you don't need a degree in physics to play detective. Next time you notice a glitch, like a song repeating on the radio just as you think of it, or a stranger wearing your exact outfit, ask yourself, is this coincidence or is the simulation winking at you? Reality's quirks might be more than quirks. They could be clues waiting to be decoded, but we're not done digging. Maybe you're convinced by Nick Bostrom's statistical odds, or perhaps the holographic principle's two-dimensional magic sold you. Or maybe you've got a wild theory of your own. Drop it in the comments. I'll be down there geeking out with you. And if your brain's still buzzing from all these cosmic possibilities, hit subscribe. We've barely scratched the surface of the universe's mysteries, and there's plenty more reality-bending content on the way. Until then, keep questioning, keep wondering, and who knows, maybe one day we'll find the cheat codes.